You know, a lot of us think of math as just this rigid set of rules you have to memorize for a test. But what if that's not the whole picture? What if we saw it as something else entirely? What if we saw it as a language? The powerful, precise language we use to describe and understand pretty much everything.
I mean, it's a massive question, right? The world is, well, it's messy. It's chaotic. It is filled with an absolutely overwhelming amount of information. So how do we even begin to get a handle on it, to predict what might happen, or even just talk about it in a way that makes sense?
Well, the answer is we simplify. We build models. Think about it. A weather forecast, an economic projection, even the route map for an airline. Those are all just models. And the universal language that we use to build them, test them, and share them, well, that's mathematics. So let's dive in and learn the absolute basics of this language.
Okay, so like any language, you've got to start with the vocabulary. And for mathematics, that vocabulary begins with the simplest ideas you can possibly think of: how to count things, and then how to put those things into groups.
So before we can even dream of building a model, we have to be able to count the parts. How many mangoes are in this basket? How many cities are in a network? The natural numbers, 0, 1, 2, 3, and on, they're our first and most fundamental tool. They are the bedrock answer to the question, how many?
All right, so we can count stuff. Now what? We've got to organize it. And that's where the idea of sets comes into play. A set is really just a collection of items. It could be the set of all even numbers, or the set of all the passengers on a plane. It's basically how we draw a circle around a bunch of things and say, okay, these things belong together.
Now, this diagram here shows a really simple but super powerful idea. So imagine the inner circle is our set of all prime numbers, and the bigger circle around it is all natural numbers. So what's all that stuff in the shaded area? That's the complement. It's everything that is a natural number but is not a prime number. In other words, the composite numbers. This whole idea of defining something by what it isn't, that's a really crucial tool for building logical models.
Okay, so we can count things, we can group them, that's great. But let's be real, the world doesn't just sit still, right? It's constantly changing. So for that, our language needs some grammar. It needs rules to describe all these relationships and all this motion. And that brings us to functions and the incredible ideas of calculus.
You can think of functions as the verbs of math. They describe actions. A function is really just a rule that takes an input and gives you one and only one predictable output. So think of a simple function like y equals x squared. You feed it a 2, boom, it spits out a 4 every single time. You put in a 5, you get a 25. It's this reliable little machine for connecting inputs to outputs.
All right, let's make this real. Picture this. A truck driver travels 2,900 kilometers in 72 hours. If you do the math, that's an average speed of about 40 kilometers per hour. So when he gets a speeding ticket near Nagpur, he's frustrated. His buddy, trying to be helpful, whips out a calculator, does the math, and says, "No way, this ticket's bogus. Your average was only 40. But then the driver explains, yeah, but he covered one 260-kilometer stretch in just 3 hours of driving, and that works out to a speed of over 86 kilometers per hour.
And this gets to the heart of the problem. See, the friend was looking at the big picture, the average speed over the whole 72-hour trip. But that ticket? That was about one specific moment in time, his instantaneous speed. And to solve this kind of dilemma, you can't just use simple averages. You need a much, much more powerful tool from our mathematical language.
And the tool for that? That's the derivative. What calculus lets us do is kind of zoom in on a single point in time, an infinitely small moment, and find the precise rate of change, the exact instantaneous speed at that one moment. This is what solves our truck driver's dilemma. It tells us the difference between what's happening on average versus what's happening right now.
All right, so the derivative is awesome for breaking things down into tiny little moments. But what if we want to go the other way? What if we have the instantaneous speed at every single moment, and we want to figure out the total distance we traveled? How do we add all of that up? I mean, how on earth do you add up an infinite number of these tiny little changes?
So look at this weird, curvy shape. How would you find the area? Well, you could start by just sketching in a few big rectangles. It's not going to be perfect, obviously, but it's a start, right? To get more accurate, you just use more rectangles, and you make them skinnier. The more you add, the better your approximation gets. So now imagine you could use an infinite number of impossibly infinitely thin rectangles. The sum of all their areas would give you the exact area under that curve.
So this whole process, this divide and conquer strategy, That's called integration. The integral is the mathematical tool that lets us do this magic trick of summing up an infinite number of tiny pieces to get a precise whole. It's really the other side of the calculus coin. It lets us rebuild the entire journey from all of its individual moments.
Okay, quick recap. We've got a vocabulary for things and a grammar for change. Now, let's put all that together to model something really big. Not just single rules, but vast, sprawling, interconnected systems. And this is where something called graphs come into the picture. The idea is so simple it's almost beautiful. You have a collection of dots, which we call vertices, and they're connected by lines, which we call edges. That's it. But seriously, don't let that simplicity fool you. This structure is powerful enough to model some of the most complex systems in the entire world.
Just think about an airline's flight network, for example. Every single city is a dot, a vertex. And every direct flight that connects two of those cities, that's a line, an edge. And just like that, this huge, messy, logistical nightmare becomes a clean, simple mathematical graph that we can actually work with.
And once you have that model, you can start asking some really powerful, really useful questions. Like, what is the absolute shortest path to get from Madurai to Delhi? And not just in terms of distance, but maybe we want the shortest path in terms of total flight time, or the cheapest path, or the one with the fewest layovers. Graphs give us the framework to solve these kinds of problems.
Now, a computer can't just look at the map and see the shortest path like we might try to. It needs a process, an algorithm. Okay, so look at the table. D0, that's our starting point, Madurai. The distance to itself is 0, of course. And to everywhere else, we just say it's infinity because we haven't found a path yet. In the first step, the algorithm looks at the direct flights. It sees it can get to City 1 in 10 units and City 7 in 8 units, so it updates the table. In the next steps, it keeps exploring connections from those cities, always looking for shortcuts. You can see it right there for City 5. It goes from infinity down to 12, then it finds a better route and gets to 8, and finally it settles on 7. After a few rounds, the numbers just stop changing, and at that point we've found the shortest path from Madurai to every other city in the whole network.
So think about the journey we just took, right? We started with something as simple as counting mangoes, we developed some rules for how things can change and interact, and we ended up with a way to model and optimize something as huge as a global travel network. That, right there, is the power of mathematics as a language.
So you see, this is so much more than just a bunch of numbers. It's literally the language we use to write the story of how our universe works, from the tiniest subatomic particles all the way to the expansion of the cosmos. And as this language gets richer and our models get better, we can describe the world in more and more detail. So the only real question left is, what amazing things will this language help us discover next?